Wait, what's the problem?
Okay. 3v3. Win. Read it for us.
Alright. In oxidation reduction, redox reactions, there is a net transfer of electrons. The species that loses electrons is oxidized, and the species that gains electron is reduced.
Okay. A whole other set of types of reactions. Redox. Something is oxidized, something is reduced. Combination of reduction and oxygen, the portmanteau. Redox.
It's like rust, right?
Yes. Let me show you real quick an example of a redox reaction. Okay. See what I have there?
It's a wire.
It is a copper wire. I'm going to mix with that copper wire a solution of silver nitrate. Dump it in there.
What charge is silver?
Silver is +1.
Okay.
So is nitrate. So is nitrate's fine. Oh Lord.
Is it gonna rust?
It's not toxic.
Is that what you think? Because when metal oxidizes,
Doing anything?
No?
Well, it's a little bit hard to see from where you're sitting. Let me try a different perspective. Can you see the top of the wire?
Oh yeah.
No.
The very top of the wire is not touching.
The top of the wire is
Oh,
copper.
it's like
The silver
cleaner.
nitrate.
The color, dude.
One is
It's
darker
like
than the
lighter
other.
than the other one's darker.
Oh wait, well, you gotta drink color.
So the copper here has not actually touched the solution. This thing's having a real hard time focusing. But we can see we've got kind of a dark situation.
Situation.
Gotta give us a situation. Darkness. Okay. The color change is evidence of a chemical reaction. Now, as this thing goes, by the end of the period, we might see something a lot more interesting. This reaction looks much better in time-lapse than it does in real time.
Well, it's time.
But what we're doing is we're actually producing silver metal.
Whoa.
That darkness on the copper wire is actually little bits of silver that are being deposited. What we're going to see as this thing reacts is we're going to see a blue color appearing. We know that blue color, we've got copper in there, that's from copper +2, just like we saw in the copper lab. We use CuSO4, copper 2+. Okay? So this is not balanced. Now it is.
Yeah.
Okay? But what we're interested in for this reaction is not really the stoichiometry. We're interested in the fact that this is a oxidation reduction reaction. Alright, so we'll let that thing go. We'll watch it for a little while. It says redox reactions. There's a net transfer of electrons. Can we see where the electrons are going in this?
No.
Not really.
Not the way we've written it, because
We forgot the
They don't have
You
to
don't
mark.
have to
we can't actually see the charges that are involved. So this is actually an example where, because this is a solid, this is an aqueous solution, this is a solid, this is aqueous. This is actually another example where a net ionic equation can be helpful to us. These are both soluble ions, so I can split them up. Now, a lot of you on the quiz forgot that if we have two AgNO3s here, we're going to form two Ag ions. And two nitrate ions.
Oh, the arc is just green.
Most of them. We're going to split up the copper nitrate, and now if nitrate is with one silver, Well, I guess unless we know silver's a +1, we wouldn't know nitrate's a -1, although we're supposed to know strong acids, right? What's an example of a strong acid that could help us remember the charge of nitrate?
Nitric acid.
HNO3. How many H's? 1. So the charge on nitrate? -1. Okay? So that means silver has to be a +1. If we have 2 nitrates combined with copper, copper's therefore
2 plus.
2 plus. And we're forming 2 NO3 minus ions. Okay? So this is the molecular. This is the full ionic. We want the net ionic. So what am I going to get rid of in the net ionic? The nitrate. We've got 2 NO3 minuses here, 2 NO3 minuses here. Same exact situation on both sides. We can cross it off. So what's really happening is copper solid is reacting with 2 silver plus ions, forming 2 neutral silver metals and the copper 2 plus ion. So there was a transfer of electrons. Who gained an electron?
Oh, gained electron.
With
Silver.
How do you know silver gained an electron?
Charge was
Positive to neutral.
If it was positive here and it's neutral here, we must have added a negative to make it neutral, right?
Yeah.
If copper was neutral here and now it's +2, it must have lost its electrons. So what really happened was that copper gave up 2 electrons to form copper 2 plus. Silver ions gained electrons to form silver metal. These 2 things that I've written down here are what we call the half reactions. They're describing half of what's occurring, right? Coppers are losing 2 electrons, silvers are gaining 2 electrons. Okay? Losing electrons, what do we call that?
Oxidation.
We call it oxidation. How do you know that? It's Leo.
That's what that means?
Says grrr. So if I lose electrons, we call it oxidation. If I gain electrons, we call that reduction. Yes, now we know why that's up there. So this is an oxidation because copper's losing its electrons. This is a reduction. Sorry, I drew this wrong. Nobody corrected me. How does a positive ion give up an electron and then form a neutral? Silver is gaining an electron. Silver ions are gaining electrons to form silver metal.
Is it about to say everyone's rewriting?
Okay. But when I think about what reduction is gaining electrons. So I labeled this one oxidation, then I went down to label silver, and it looked like it was losing an electron, and I said to myself, wait a minute, it's not an ox-ox reaction. It's a redox reaction, right? It has to have oxidation and reduction together. Somebody has to be losing electrons, but somebody has to be gaining those electrons. We can't have electrons just flying off into space. Okay? Now, sometimes they might give you these 2 half reactions and ask you what is the overall balanced reaction.
We have to include the.
So we're going to combine these 2 reactions, right? But here's the thing we want to do when we combine them. When we combine 2 half reactions, we have to make sure that the total number of electrons are the same because we don't want the electrons to appear in the overall reaction. So in order to do that, if this thing is losing 2 and this thing's only gaining 1, we need to do this reaction twice. Then when I add them together, the 2 electrons we lost have both been gained by somebody else, and so the electrons don't appear. So we'd end up with this overall reaction. Starting to form what I'm trying to form. Very fine little crystals of silver. And a longer this thing goes, the longer those crystals are going to be. Okay? So this is a pretty simple, pretty common example of a redox reaction. A more complicated, actually before we do that, let's talk about part B here. It says oxidation numbers may be assigned to each of the atoms in reactant and products. This is often an effective way of identifying the oxidized species in a redox reaction. So we have to talk about what are called oxidation numbers and how to assign them. There are rules. Rules for assigning oxidation hashtags. Numbers, it's the numbers section. Oxidation pounds, yeah. Okay. Now, the rules are in your book, and I'm going to find them. Is it in 18 point? I'm going to use the glossary.
When you went chemistry lesson, did you use a textbook or was it lecture?
Everyone shared one.
Well, we didn't use the internet because not everybody had the internet.
But
Okay, so oxidation, 70, 170 is where we're going to find.
The giving and donating.
Okay, so page 171, guys, is where you're going to find these rules in case you lose them.
These are electrons.
the moles just,
So it's not acid or
no, I'm just saying.
Everybody wrote that down?
This is what he's gonna
Right.
talk about.
Everybody wrote down what I just said.
Page 171.
Page 171 is where you find these rules for assigning oxidation numbers. So I'm just going to put them up there, and you guys are going to, at your leisure, copy them.
Le jour.
Yeah, means on your own time. So an atom in an element is 0. What do we mean by that? An atom, when it's in its elemental state, it's 0. So if we have O2, that's its normal elemental state, the oxidation number of oxygens in O2 is 0. Copper, this is in its elemental state, so it gets an oxidation number of 0. Silver on this side is in its normal elemental state, it gets an oxidation number of 0. Second rule is that a monoatomic ion is the same as its charge. So silver here, its charge is 1+, its oxidation number is +1. Over here, copper 2+, its oxidation number is +2. Usually when we're doing charge, we put the number first. When we're doing oxidation state, we put the plus or minus first. That's how you know which one you're talking about. Okay? So in this case, we could see if silver went from a +1 to a 0, well, if it's getting less positively charged, it must be gaining negative charges, right? If it's gaining negative charges, we call those electrons. Gaining electrons is reduction. Copper went from a 0 to a +2. The only way to become more positively charged is to lose your electrons. If it lost its electrons, then it's undergoing oxidation. So we didn't even have to write these half reactions. We could just look at the oxidation numbers and know which one is gaining electrons and which one is losing. Okay, now the next rule, these go in order. The next rule, you would look for any fluorines. If you have fluorine in your reaction, give it a -1. That's because it's the most electronegative element. Then, when we go to oxygen, oxygen is typically going to be a -2, not a +2 like some of you drew in your crazy Lewis structures on that one quiz. We had oxygen with 4 bonds. Oxygen normally forms a -2. Okay, but there is one exception. When it's in a peroxide, like H2O2, hydrogen peroxide, it's actually a -1. Okay, and then the last rule is that hydrogen is a +1 when it's covalently bonded to somebody else. talks about in the last part of this section, it says there are a number of important redox reactions. This is part E of your outline. In energy production processes, combustion of hydrocarbons, metabolism of sugars, fats, and proteins, etc. So let's look at a combustion of a hydrocarbon. CH4 reacts with oxygen, forms carbon dioxide and water, H2O. Again, just looking at this, can I tell that electrons are being transferred? No, there's no electrons in the reaction, right? So we have to assign oxidation numbers in order to figure out which thing is being oxidized and which thing is being reduced. So we start at the top of the list. Any atoms in their elemental state? Oxygen, it's O2, right? I mean, it doesn't make sense for this thing to be anything but a 0, right? Because there's no overall charge on this thing. Okay, so oxygen here is 0. Next, do we have any monoatomic ions? No. Do we have any fluorine? No. Do we have oxygen?
Yes.
Yes. In its compounds, it's usually a -2. Now, is this a peroxide? No. They would tell you the name peroxide. I would have said this is carbon peroxide if I want you to treat this as a -1. This is carbon dioxide, so we assign the oxygen -2. In water, H2O, we also assign the oxygen a -2. I don't like that H. Okay. Next rule, hydrogen is a +1. Well, that makes sense because if we assign the hydrogen +1 and there's 2 of them, the oxygen being a -2, they add up to the charge, which is 0. That's a rule that's not really written here. The last thing is, whatever the total sum of the oxidation numbers is, has to give you the charge on the overall substance. For example, the sulfate ion. The first rule I'm going to encounter when I'm assigning oxidation numbers to the sulfate ion is oxygen. We give oxygen a -2. What's the charge on sulfur then, or the oxidation number on sulfur?
+6.
Has to be +6 because we've got 4 -2s, so that's -8, but we still have to have an overall negative charge. So sulfur here would have to be +6. Sum of the formal charges should give you the overall charge on that substance. Okay, that's a rule that's not in there. We're going to see that again in a minute. Because I've assigned my hydrogen +1 here, I'm going to assign a +1 there as well. So now, we don't have a rule for carbon. Now we have to say, well, let's look at everything else, and let's see what carbon has to be. If carbon's with 4 hydrogens that are each +1, carbon has to be -4. Over here, carbon's with 2 oxygens that are each -2, so carbon here has to be +4. Okay, so now the question is, what element was oxidized and what element was reduced?
Oxygen was oxidized.
Carbon was oxidized.
Wait.
Oh, my bad, yeah.
Yeah.
Oxygen was reduced.
Yeah, oxygen
And then
was
carbon
reduced.
was oxidized.
Oxygen went from a 0 to a -2. What did it do?
Gained
Gained electrons. Grrr!
Okay.
Reduction. Oxygen underwent the process of reduction.
And carbon underwent oxidation. In no way are those things confusing.
Now carbon went from a -4 to a +4. How do you do that? How do you get less negative? Give away your electrons. Losing electrons. Losing electrons.
Yeah.
Oxidation. So carbon was oxidized. Okay. If we talk about the species that it's in, we could say CH4 was the species, the molecule that underwent oxidation. We could say that O2 was the molecule that underwent reduction. Okay. There's also these other weird terms that we use called agents. We have oxidizing agent and reducing agent. Well, if carbon was oxidized, who caused that? Oxygen. Right? That makes sense. It's being oxidized, it's being combined with oxygen, right? But we could say this thing is oxidized, which makes oxygen the thing that caused it to be oxidized. We call this the oxidizing agent, even though it was itself reduced. O2 underwent reduction, but it couldn't have done that unless it, let's see, reduction is gaining electrons, right? It had to gain them from somebody. Who did it gain them from? Carbon, right? So we can consider CH4 to be really the agent that caused that reduction. I give the analogy like if I give Osama $1, that's a transfer of money, right? Here we're talking about transfer of electrons, right? Did I make you richer or poorer? Richer, so I'm the richifying agent. I'm the agent that caused somebody to become richer. But did I myself become richer? No, I was purified.
Beneficiary.
But I purified in order to make somebody richer. So I underwent purification, but I was the agent of richification. Carbon underwent oxidation, but it did so in order that oxygen could be reduced. So CH4 is actually the reducing agent. Oxygen underwent reduction, but it caused this thing to be oxidized, so this is the oxidizing agent. So they're sort of flip-flop with each other. Okay? You guys are typically going to have to just tell me which thing was oxidized and which thing was reduced.
But which thing oxidized the reduced?
What's that? All right. The other thing you're going to have to do, sleep. Yes, you will have to sleep at some point. Part C says balanced chemical equations for redox reactions can be constructed from tabulated half reactions. So, if I give you a table of half reactions, you're going to have to be able to combine them to make an overall reaction.
Where did you read that?
Part C. And here is a big, beautiful table of a bunch of half reactions.
Oh,
I remember that.
I don't even want to put my glasses.
So if I were to do, say, something like this, if I told you that I was going to react potassium permanganate and copper metal, and I wanted to form Mn2 plus and copper 2 plus, I want to know what that balanced equation looks like. There's actually no way to balance this reaction as written. Because I don't have any potassium on the right side, I don't have any oxygen on the right side. Okay? You're not going to have to balance this. What you're going to have to do is look at these things and look at what they turn into and figure out where is there a half reaction that describes a similar process. So, you will not find KMNO4 on here because K is going to be a spectator in this case. But there's lots of reactions that have an MNO4. Here's one. Here's one. Well, there's one on the bottom, MNO4. Okay, but they each form something different. This one forms MNO4 2 minus. This one forms Mn2 plus. This one forms MNO2. I said I wanted to form Mn2 plus. So let's write that reaction. MNO4 minus plus 8 H pluses plus 5 electrons yields Mn2 plus and 4 H2Os. Right? There's a whole bunch of stuff in that half reaction that we never would have even seen up here. Now there is a process of actually coming up with this that you used to have to know. 4 really complicated steps. The sweet acronym that I came up with. Yoke!
It's a real helpful one.
It's the best acronym ever. Okay. Fortunately for you guys, you don't have to do that. You just have to look and say, do I have a reaction that has my reactant and my product in it? Boom, write it down. Okay. Do I have a reaction that has copper and copper 2 plus in it?
That one on the right side. Wait, no.
C2 plus.
Where?
Yeah.
The C2
No.
plus one?
No, it's going to, oh, well,
We got CO2 plus and we have copper.
Yeah.
I remember the
There's a problem.
What's it?
you go the other way.
It's going the wrong way.
So flip it.
So can we just?
Can you flip it?
You must flip it. Because if you look at the top of this, which you can't really see, This is a table of standard reduction potentials. Everything on this list is going to be a reduction reaction, but there's no such thing as a red-red reaction.
You got an oxide.
There's a redox reaction, yes. So one of these we're going to have to flip to turn it from a reduction into an oxidation. All right, what we're going to learn in the next section is actually what to do with these voltages. So let's talk about this a little bit. These cell potentials, this E0. It's got a V in it because it's the voltage. This one, it says, has a voltage of 1.5. When this reaction occurs, the change in energy of those electrons is for them to gain 1.5 joules per coulomb of electron. Physics people, you know what a volt is, right?
Yep.
A joule per coulomb. So the electrons are gaining energy by this reaction. When copper plus 2 ions gain electrons, forming copper metal, they also gain energy, 0.34 volts. Now, like I said, we can't have two reductions. We've got to reverse this one. So let's reverse it to make it an oxidation. Well, that's going to be copper turning into copper 2 plus 2 electrons. What's the voltage of this going to be? It's going to be the opposite. If this reaction causes something to gain 0.34 joules per coulomb, going in reverse, it's going to lose 0.34 joules per coulomb, or 0.34 volts. Okay? So what we're really interested in combining is this reaction, which is an oxidation, with this top reaction, which is a reduction, so that the sum of them will be a redox. But what do I have to do first? Look at the reduction. Look at the electrons. How many electrons are being gained in the reduction? 5 electrons being gained. In the oxidation, how many are being lost? 2. So if I'm only losing 2 electrons, where do the other 3 electrons come from? Okay. In writing a balanced redox reaction, the only thing you really have to do is to balance the electrons. So if I've got 5 electrons in this reaction and 2 electrons in this reaction, how am I going to balance it? I'm going to multiply this one by 2, and I'm going to multiply this one by 5. So I'm going to get 2 MnO4 minus plus 16 H pluses plus 10 electrons yields 2 Mn2 plus and 8 H2Os. And I'm going to add to that a reaction where 5 coppers give us 5 copper 2 pluses plus 10 electrons. When I add these two together, I just add up everything on the left side of the arrows. I add up everything on the right side of the arrows. So 2 MnO4 minuses plus 16 H pluses plus 10 electrons plus 5 Cus yields 2 Mn2 pluses plus 8 H2Os plus 5 Cu2 pluses plus 10 electrons. Just like what we talked about with spectator ions, if something's present in both forms on both sides of the reaction, we cross it out. So because we have 10 electrons here and 10 electrons here, we cancel them out, and this is our balanced equation. All right? Now the only thing that can get a little bit more complicated is if you have multiple reactions that are involving H+, right? A lot of these things have H+ going on in them. So what you might end up with is some H pluses on one side, other H pluses on the other side. So if I had 16 H pluses on the left side and I end up with 6 H pluses on the right side, then only 10 of them actually underwent a change, right? So you can cross off some of the species if they're present on both sides. If I have 8 waters on the right side, but I had 4 waters on the right side, on the left side, then I only really formed 4 waters, right? Because I had 4 to begin with. So you might cross off the 4 on this side and change this 8 down to a 4. Okay?
Wait, I'm confused. So what do we do with the voltages?
Oh, voltages.
That's for determining.
Glad you asked. Well, remember what we're really combining is this reaction, which causes our electrons to gain 1.5 volts, with this reaction that causes them to lose 0.34 volts.
Well, you gotta multiply the energies too.
What?
Don't you have to multiply the energies too?
No. Because what is a volt?
It's the joule per coulomb.
Joules per coulomb. What's a coulomb?
Coulomb's charge.
It's an amount of charge. It's actually an amount of electrons. So it doesn't matter that this thing has 5 electrons in it, because this is already the amount of energy gained for a certain amount of electrons. If I double this, I'm going to double the energy and I'm going to double the number of charges. So this is still going to be the same. Still the same number of gains of energy per single little charge. If I did this 100 times, the joules would be 100 times more, but so would the number of coulombs. So it's still going to be the same voltage. So to get the voltage for this one, I just add them up. 1.51 volts from the reduction plus negative 0.34 volts from the oxidation gives me an overall potential of
1.17.
what?
1.17.
1.17 volts. Okay? Questions? Well, I hope that fit. Still going?
Yep.
Yeah!